Hi, we're continuing our discussion with the MOS transistor theory. And just to repeat or stress on what we mentioned in terms of solving the DC problem for questions that involve transistor. And much like, for example, the example we solved here. And basically, what's the general strategy? I want to make sure that we review this at the beginning of this lecture. So the very first thing is that calculate or determine um, all voltages that you can, right? Because in particular, we need to know the VGS and VDS and uh, so because we need them for the next step. So the next step, determine if the transistor is off or it is on. Okay. Now, if it is on, it is in linear or is in saturation. Okay. And based on that, then you can determine the current equation, right? And then use this current equation to find the unknown in the question. Okay, so that's one point. The other point, I did not explain this example very well. So last time, kind of, I assumed that VD was known, but in this problem, the appropriate sort of steps is to determine the region of the transistor, which is saturation, and then we apply the current equation to find VDD, okay, which is this point, and then determine R, okay. So that I wasn't, or I did not spell it out very clearly in the last lecture. Okay, now with that said, we move on to the last section of this chapter, which is the DC characteristics. And the DC characteristics basically will talk about the pass transistor, the DC response, and some of the noise issues. Now, one important thing is that we need to understand. Let us go to the whiteboard and do some quick discussion on this thing. We kind of need to understand. One might ask why the transistor. Now we will start to study and see more and more of our conventional basic circuit, which is the inverter. And the inverter consists of the following. The very first thing, you have the PMOS here, okay, and then you have the NMOS, and you find that the PMOS is on top and the NMOS is at the bottom, okay, and this is the input, this is the VN, and this is the V out, okay. And the question that occurs here, or somebody might ask, why not have the transistor look like this? The NMOS is on top and the PMOS at the bottom. Okay, this is a valid question. Why not? Why not all the transistor has two NMOSes? Why not like having this is an NMOS and this is an NMOS, or both PMOS? Why the correct configuration is this configuration? PMOS on top and NMOS at the bottom. Well, the reason for that is very simple, actually, and we'll explain this in quickly. Um, First of all, let's assume that we want to charge a capacitor through a PMOS. So here is a PMOS connected to VDD, and this is capacitor, and this capacitor initial voltage of this capacitor at time 0 is 0. So we would like to charge this capacitor, and if we do that, of course we have a 0 volt here, and if we do the analysis, we will see that this node, this VC, will charge all the way up to VDD. Okay, good. All right. Now let's do the same thing for the NMOS. And so let's say, for example, I have an NMOS here, okay, and I have a capacitor here, and let's say we have here VDD to turn on the NMOS, and we'll try to charge the capacitor here. And notice that here, that the output here, the VC here, which is initially 0. Now notice that VGS here, VGS for this transistor is defined as the VDD minus VC, which is the output node right here. And therefore, what you will see is that this capacitor, the output node or capacitor will charge up all the way to VDD minus VT. And the reason the minus VT, so that we maintain VT here, the input must, or the gate must have a VT voltage higher than the output. So the output will be charged up all the way to VDD minus VT. Well, that's not cool from the NMOS, because you see the PMOS is charging VT all the way up to VDD, but the NMOS is not charging that way. So we consider the NMOS a bad charger. And the NMOS, the NMOS is a bad charger, and the PMOS is a good charger. Okay, all right. So that's that's the first piece. Let's go to the second piece here. Let's assume now that we are trying to. Whoops, sorry. Let's assume that we are trying to discharge a capacitor here through a PMOS. Okay, so this is a PMOS here, and this is the capacitor here. And this VC initially is at VDD, equals VDD, and what we try is, so this is a 0 volt to turn it on here. So and similarly we'll do the same exercise for the NMOS, and here's a VDD here. Okay, and this is, whoops, okay, and this is VC initially at VDD. Okay, now, so what we have here is the current through the PMOS. Notice that the PMOS, the current goes from here to here. So this is the source and this is the gate. So the source and the gate, there has to be a VT differential between the two of them, and therefore the output will discharge all the way not to 0 volt, rather to VT of the PMOS. Okay, and here, by the way, VDD of the minus VT for the NMOS. This is the threshold for the NMOS here. Okay, so we'll drop this VDD, discharge it all the way. That's too bad. We would like to have a 0 volt here, a discharge. If you look at the NMOS, the VGS here is completely isolated from the output. So the VGS here equals VDD. So we will discharge this capacitor all the way to 0 volt. Okay, well then notice here. Notice what? Notice that the NMOS is a good discharger, and the PMOS is a bad discharger because it discharged all the way to VTP. Okay, so notice a good charger, the PMOS, a good discharger, the NMOS. Therefore, this explains the NMOS, the PMOS to charge because it's a good charger, the NMOS to discharge because the NMOS is a good discharger, and therefore this is the configuration of the inverter. The PMOS is on the top and the NMOS is the bottom. Okay, let's go to the lecture now. Okay, so now, okay, what we're seeing here is that he's saying that as far as pass transistor, if we are trying to charge here, so this node will be charged VDD minus VT. Again, why is that? Because when you have this current flows this way, this is your drain, this is your source, you have to maintain a VT differential between the gate here and the source. And once it reaches charging this node to VDD minus VT, this transistor shuts off. It will not be able to continue charging above VDD minus VT. Okay, so and this is what we talked about earlier about being the NMOS a bad charger and the PMOS a bad discharger. Okay, so it discharges here the node all the way to VT of the PMOS. Now you can see here he's trying to be a little So you can see that we try to charge the output all the way. This node here, it will be charged from this node. So, and this is VDD, 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 and you will see that eventually this node is charged VDD minus VTN. And notice that we would like always for these transistors to maintain this VT differential voltage, VT differential voltage, to keep the transistor on. Okay, if you don't maintain VT, the transistor shuts off. If you look at this configuration, this node will be charged here to maintain a VT here, a VT differential voltage to VDD minus VTN. Now notice, for this transistor to stay on, you have to keep differential voltage between what? Between the gate and the source. And therefore, this will be charged by VDD minus 2 VTN. Okay? Now, and this is the transistor that we will study, its DC characteristics, and you can see that the current here flows through the NMOS to discharge and through the PMOS to charge. Now, here as this voltage in the input changes, you will see that the NMOS goes through cut-off linear saturation based on the value of the Vn. So if the Vn is less than the threshold of the Vt of the NMOS, you will see I'm sorry. If the Vn is less than the Vt of the NMOS, you will see that the NMOS is at cutoff. But once the Vn goes above the Vt, then you are either in linear or saturation for the NMOS. How do I know? Well, if the VDS less than VGS minus VT, then you are in linear. And if we evaluate VDS for the NMOS based on the equation, we will find it's V out less than Vn minus Vtn. And if VDS is greater for the NMOS greater than VGS minus VT, you are in saturation. And if we evaluate it in the equation, we will find out that this is the V out greater than Vn minus VT. And you can do similar analysis for the PMOS. The message here is that changing the value of Vn moves the transistor in different states for the circuit. And this transition, it's preparing us for the transient analysis on next chapter. See, this chapter is DC analysis, or where voltages are constant, but now we starting to talk about cases where Vn changes, and this sort of prepares us to the transient analysis. Okay, if we plot the current for the NMOS, all right, with different VGS, we will see this type of curve which we have seen before. Of course, there is this linear region and there is the saturation region, and similarly the current through the PMOS, but it's in the negative value. We said the PMOS always has negative values. Okay, now if we flip those curves and bring it up here, basically we take the inverse of, or the negative of the current, and this is because we are trying to set IDSN equal to the current through the NMOS equals the current through the PMOS, and then we shift these curves so that we are plotting V out, which is coming out of the NMOS equation and coming out of the PMOS equation. So we do this shifting, and we will see this overlap between the curves for the NMOS and the PMOS. And the intersection point here, really, you will see that these are the operation region, and you can see that the IDD, which is the current through the NMOS and the PMOS, becomes of this nature, this curve here. Okay, they are the intersection points of these curves. You can see them, how they intersect. Okay, now, which brings us to, from that we can deduce the characteristic curve, the characteristic transfer curve, and this which plots V out against Vn, and this is basically what we are after here. It is to understand how the output changes based on the input. Okay, after all, I have a system where I'm providing an input voltage. I would like to understand what is the value of the output voltage. Now, this is here the slide that talks about the characteristic voltage for oops, sorry, the characteristic the transfer curve, and you can see that here is V out versus Vn. And you can see as Vn moves from 0 volt all the way to VDD, the device moves into different region A, B, C, D, E. And in these regions, the NMOS and PMOS behave differently. So for example, when Vn, when V, we are in region A, the input voltage is between 0 and VTN. It's small voltage, it's small, the input voltage is big. So in this case, the NMOS device is an off state, the PMOS is in linear, and the V out equals VDD. And basically what happens is that you have a current supplied from the VDD, and this guy is off the NMOS, and so the output is equals VDD. Now, if we raise the input a little bit above here, we will turn on the NMOS device, and it will be in saturation, and the PMOS is still in linear, and the output is greater than VDD over 2. Okay, so we will start seeing the output drop a little bit. Okay, so the V out is less than VDD, but is greater than VDD over 2. So you can see that this is the V out start to drop here. Okay, let me use another color here. So you can see the V out start to drop here at the B region. Now, once we have the Vn equals VDDN, we go to the C region here, and both the NMOS and PMOS are in saturation, and in this region, the output drops sharply. And we call this, it has the highest gain. This region has the highest, because the two transistors in saturation, we have the highest current in both devices. Now, if we move to VDD to region D, where the input is more than half of the VDD, but less than VDD minus VTP, okay, which is this one, we'll see that the PMOS is in saturation and MOS is in linear. Now, if we increase the output here, will be less than VDD over 2. Now, if we increase the output more than between VDD and VDD plus VTP, remember VTP here is negative value. Okay, so between VDD and VTP, I'm in region A, where the PMOS device is in cutoff, and the linear the NMOS is linear, and the V out is 0, because in this case this PMOS is off and the NMOS is on, and we are completely discharging the output. So these are the most interesting regions really. This region A, where the NMOS is off and the PMOS is on, region E, where the PMOS is off and the NMOS is on, and region C, where both these the NMOS and PMOS are in saturation, and we call this region has the highest gain. Okay, and the gain is defined delta V out over delta Vn. All right, so you can see a small change in the input changes the output dramatically. Okay, all right, so okay, now what we would like to compute here is something called Vn, and Vn is the voltage when the transistor input and the transistor output have the same voltage value. Okay, the input and the output of the of the inverter, I'm sorry, has the same value. We call it Vn. So we'd like to compute this. So it occurs in the C region, where both transistors are in saturation. So we compute the current equation in the NMOS, all right, and we compute the current equation in the PMOS, and whatever current goes in one device goes into the other device. So we equate these two equations and we solve. We get the value. Notice Vn is somewhere here, so because it is either in the source and the drain of one device or other, and then we solve the equation. A little bit math involved here. Consult your textbook and find out the solution. But Vnv equals VDD plus VTP plus VTN 1 over R over 1 over R. Now R equals, watch, R equals beta P, for the PMOS over beta for the NMOS. Now what is beta here? It is W over L for the PMOS times COX times the mobility for the holes over the W over L for the NMOS device times COX times mobility for the NMOS device. Now typically the COX cancel COX, and typically the mobility for the NMOS is higher than the mobility of the PMOS by 2 to 4 times. 2 to 3 times, sorry, and it is always it is typically desirable to have this R around 1, because if you keep this R around 1, watch what happens. This becomes 1, this becomes 1, and VTN, which is typically the negative of the VTP, this cancels out, and then you get VN equals VDD over 2. This is very desirable, and this happens when R equals 1. And to have R equals 1, right, the size of the PMOS has to be 2 to 3 times the size of the NMOS. Okay, all right, and this is coming really from the fact that the mobility of the electrons is 2 to 3 times higher than the electrons. If you consider velocity saturation, you will end up with a different expression. In fact, the square root goes away because of the velocity saturation. You can go through the math yourself. Now, if we look at the characteristic curve where we plot the V out versus the Vn, okay, what is the impact of the ratio of the PMOS over the ratio of the NMOS? Okay, so basically this beta of the PMOS and beta of the NMOS, it indicates how powerful the device is. You can see if the NMOS is very powerful, and we can change the power of a device by changing the W over L for the NMOS or the W over L for the PMOS. If we increase this for the PMOS, it becomes powerful. If we increase this for the NMOS, it becomes powerful. If you have a powerful NMOS, you will see that the droppage happens quicker. If you have a powerful PMOS, you will see that going up the charging becomes quicker. So we kind of move the characteristic curve left and right based on the strength of the device. Now, it is interesting to see that the device, the inverter, works fine. Never mind moving this curve right or left. It always stays an inverter. And that's why we say that the CMOS is a ratioless device, meaning it does not depend on these sizes. Yes, these sizes impact the performance, but they do not impact the functionality of the inverter. The inverter always will be inverting the signals. Okay? Finally, the final topic we'll discuss here is the noise, and basically the noise is important to compute in circuit, and we would like to talk about the noise margin. If you have an output here, an inverter which produces an output voltage here, so at value high, so this inverter produces a value output high, and it is the value of the output when we consider the voltage high, and the input that is considered as high for the next inverter, we call it VIH. Now, the difference between VOH and VIH, this delta is, we call it noise margin when the signal is high. Similarly, when this inverter sends out an output which is low, right, which is this one here, and this inverter interprets an input which is low, which is here, the differential between the output and the low output of the driving inverter and what is being interpreted as a low input for the receiving inverter, this delta is considered to be noise margin low. Of course, this is important because we would like to maximize the noise margin. The wider the noise margin, the better it is. Because wider noise margin means that my circuit can tolerate more noise. And let's suppose, for example, that I have noise margin high equals, let's say, for example, 0.2 volt, and noise margin low equals 0.25 volt. If I inject a noise of 0.1 volt into the system and the sources of the noise are plenty in circuits, it means that my circuit will tolerate this. But if I inject a noise of 0.5 volt based on this characteristic, it means my circuit will fail. Okay, so the noise margin is an indication of how much my circuit can tolerate noise, and the sources of noise in circuits are plenty. Okay, so it is important for me in my circuit to maximize the noise margin as much as I can. Okay, here is another definition of somebody will say, where is these the output when it is high and the output when it is low, the input when it is low, the input when it is high. Typically, the VOH in MOS in CMOS circuit is considered to be VDD, and the VOL is considered to be 0 volt. Now, the VIL and VIH, we have to go to the characteristic curve and look for the point where the slope is -1, and when we go down here, and the first one, it is considered, this point considered VIL, and the second one is considered to be VIH. This is by definition, by the way. So again, a reminder, noise margin when the output is high or when the signal is high is VOH minus VIH, and noise margin when the signal is considered to have low value, VIL minus VOL. Okay, with that, we conclude this chapter of transistor theory. We'll see you in the next chapter, and thank you very much.